In this video, we're going to talk about the basicity and preparation of amines. We're going to go to describe the best exam answer for if you're talking about why they are bases, and we're going to talk about the preparation of amines and the reagents and conditions of those, as well as the reactions with acid. So amines are alkaline, and the nitrogen in the amine acts as a proton acceptor. So if you look at this equation right here, you can see we have ethylamine, here, 2 carbons, and then there's your amine group right here. You see there's water, and the water has donated a proton, so it's acting like an acid. Because it loses that proton, becomes OH-, which you can see in the products. And then this nitrogen here accepts it, and that's why it turns into NH3+. And normally when nitrogen accepts a proton, it will become positive if it was neutral in the first place. But why does it do that, and what about the exam question? So that what's really important, okay, is this pair of electrons. Okay, so you've got a lone pair of electrons which is on the nitrogen, that accepts the proton. Now that then leads into our exam answer and our exam tip. The exam tip is the ethylamine. In this case it could be any amine, but in this case ethylamine has a lone pair of electrons, and we've highlighted that here on the nitrogen, which accepts a proton. Normally what students do is when they're asked to say why amines are a base, they just say accepts a proton, doesn't get the mark. You have to refer to the lone pair of electrons on the nitrogen as well. So both parts will give you the full marks on this question. Moving on from the basic properties of amines, we can now see how that can link to formation of salts. So because they're basic, they can form salts with an acid. Now, if you remember the definition of a salt is when an acid has its hydrogen replaced, substituted by usually a positive metal ion or an NH4+ ion, or in this case, it's going to be with our positive amine ion. Okay, so let's have a look at a simple example. This is methanamine, and this methanamine is going to be added to a strong acid here, HCl. The HCl is going to donate its proton. Remember that accepts it because there's a lone pair of electrons on the nitrogen that can accept that proton. Both of those need to be said. And then we make this salt of CH3NH3 and the Cl-. Now, really important, a really good check if you're doing equations, always check that the charges on each side balance, and if they do, it's a good chance that you've balanced it correctly. Okay? Now they are balanced because this is neutral on this side and this is neutral on that side. If you're not sure though, you can draw it in displayed formula, and sometimes that makes it a bit more clear. So here's our methanamine. There's our lone pair of electrons that can accept the hydrogen from the acid. Okay, and then a really important thing again as well, if you've got nitrogen and it has 4 bonds, generally has a plus on it, so it's quite a good little tip. Okay, and that is your positive ion. Now, that then can be put around brackets and then Cl-, but don't worry about the brackets if you're doing structural formula. It's just if you've got this big displayed formula here. So if we then move on and we show a different acid this time, and the different acid is going to be sulfuric acid. So sulfuric acid, again, if it's a 1-to-1 ratio you see here, you can see it can donate a proton. And you get the HSO4- negative ion, and you get the CH3NH3+. Again, so you've accepted a proton because this lone pair on the nitrogen. But there's a little complication, and if you want to get the highest grades, you need to be prepared for these little complications. And if they indicate in any way that the acid is fully dissociated, because this is not fully dissociated, it still has 1 proton here. Okay. If there is indications that it's fully dissociated, and that can be through ratio, or it can be through they tell you, you can see that here both hydrogens have gone from the sulfuric acid. See, it says SO42- there. So both these hydrogens have gone. Now, if you see this ratio, you can see that I'm going to get both of those protons pulled off the SO4. Now, generally in exams, they kind of accept both, but just be prepared that you've got an acid that is diprotic, for example, even if it was triprotic, you could get a slightly more complicated version of these equations where you have more than one molecule of the amine that is protonated. Next, going to do the synthesis of those aliphatic amines. Now that is done with excess ammonia and ethanol. Now ethanol is a solvent because it prevents substitution by water, because water is also a nucleophile, and this is nucleophilic substitution, and we'll show you that in the next slide. Okay, but really, really important, and I will say this in my exam style questions video, is that actually a lot of the time the questions on this are based upon remembering the reagents. So that's why these are highlighted. Make sure if you want to make an aliphatic amine, do it with excess ammonia and ethanol. Okay, and that's with a halogenoalkane. So let's choose a simple halogenoalkane, bromomethane. We've got bromomethane, and we've got the absolutely simplest amine you can ever come across, which is ammonia. Again, the ammonia has a lone pair of electrons. Those lone pair of electrons then come in and bond with the carbon, but we'll show you that mechanism in a second. They create our amine, okay, our primary amine, which is methanamine, and HBr. So again, what kind of questions you're going to get? You're going to get the reagents. You're going to get, can you give a full balanced equation? So just remember, your product can be HBr. But what I'll also say is your product sometimes can be different if there's an excess of ammonia. So if there's an excess of ammonia, then the ammonia can react with the HBr and create NH4 plus, Br minus, okay, ammonium bromide. But we'll, again, talk about that slightly later. Now let's look at the mechanism. So the mechanism is nucleophilic substitution. So the type of reaction that we're having, the type of mechanism, is nucleophilic substitution. So if you're asked to describe the mechanism, nucleophilic substitution. Now, what we do here is as we do normally, which is the dipoles, and that's because bromine is more electronegative than the carbon. Okay, and then we have our ammonia, and then from our ammonia, you can see the arrow goes from the electrons to the plus. And then it kicks out from here, okay, and kicks out the bromine. That then creates this intermediate. You can see this positive intermediate. Here we've got, again, these 4 bonds to the nitrogen, so it's going to be positive. Okay, and then we want to get rid of that positive to make our amine. And so what we do is we take the electrons out of this bond and put them back in to cancel out this positive charge. Remember, one of these electrons in this bond is from the nitrogen, one is from the hydrogen. So the nitrogen's electron is returning back to itself, and then the extra electron is cancelling out the plus. If that is the case, that H is going to turn to H+, which is going to react with this Br- that's created here, and that's where you get your Br- product. Okay, now, if you then look at it now, remember, as I said, Br reacts with that H, that's where you get that, and then this H gives the electrons, this NH bond gives the electrons that creates your amine. Now, this is a simple nucleophilic substitution mechanism, and you can have the same if you're doing OH minus aqueous that is added to a halogenoalkane to make an alcohol, which is nucleophilic substitution. It's almost exactly the same. But you don't really go over this mechanism in much detail, but I'm showing you this to show you what happens with the further products of this, because what I haven't shown you is that the amine you make, this is really important, has a lone pair of electrons. Now that theoretically means that it can do exactly the same thing that that nitrogen is doing right now. So imagine this is all in a pot. This is all in a pot, so I've added this, I've added to the ammonia. It's going to make this, which is then going to turn into this amine. So the amine is in the pot with the ammonia and with the bromoalkane. So let's think, what would the amine do? And think to yourself, what would the amine actually do if it was still around some halogenoalkane? So let's have a look. Well, there's your amine that you've made. Let's do our dipoles again. It would do exactly the same thing. Hopefully you can see there's a pattern. It would do exactly the same thing. So it would start actually reacting. Again, there's too many bonds, this nitrogen, so we're going to just get rid of one of them. Okay, there we go. that cancels out the positive, okay, and then we have this amine here. So theoretically, if you add a halogenoalkane to ammonia, not only can you make this primary amine, you can make this amine down here, which is a secondary amine, which is diethanamine, so dimethanamine, okay. Now, this dimethanamine, there's only one carbon there, one carbon there, okay, can then also do the following. It's got a lone pair of electrons, so maybe it can do the same. So that means it also creates that HBr, there's that lone pair. That means it can then do exactly the same thing and then bond in again. Now this creates a kind of series of reactions which we'll just go through now. So imagine your first reaction is your NH3 going to your primary amine. Our second reaction is then if I've got this CH3Br still around, I've still got this one with my lone pair of electrons, which is going to do the same thing, going to bond in. And then potentially it could do it again, because that still has a lone pair of electrons, still can do nucleophilic substitution with the bromoalkane, okay, and theoretically might even be able to do it again, but don't worry too much about that. So essentially what we're saying is it can do it two times further. So that one, and that one, all in the same reaction. So you're going to get a mixture of products. Now, how do you stop getting a mixture of products? And that's the key thing, and that's there's two types of questions that can come from this. One is sometimes they ask you to predict what this is going to be, and we'll go through an exam-style question on that later. But the other one is, why is there excess ammonia? And I'm going to explain to you why there is now. So I find this easier when I'm in class. I find it much easier if I just do these as different coloured balls. So our CH3Br is a red ball, NH3 is a blue ball, and our CH3NH2 is a yellow ball. And I told you they're all in one pot. So here is our pot. So we've got our pot. We start off with excess ammonia because it says excess ammonia there. That is your condition, excess ammonia. So I've got more blue balls than I've got red. So the red balls are the halogenoalkane. And that's roughly a ratio of 1 to 2 at the moment. So that means I have an excess of ammonia 2 to 1 in this pot. And that works, that's the way it's meant to work. Now if that happens, the NH3 is in excess, okay? And that is how I'm meant to do the reaction. Now, if I do another reaction, but this time I do the ratio the other way around, and if you look at it, I've got the red balls, this is the halogeno again, so I've got the halogenoalkane, and then I've got the NH3s. And that means the CH3Br is in excess instead. So I've got one pot with the NH3 in excess, one with the CH3Br. Let's first look at the NH3 in excess and see what happens. So the NH3 in excess is going to convert into our amine. Our amine is yellow. So let's take one of our blue balls and one of our red. One of each is going to create a yellow. That's all we've done, taking one of those, and created a yellow. That means we've still got ammonia around. Okay, so ammonia is still flying around, but the ammonia has got no halogenoalkane to react with. It's got nothing at all. So the reaction essentially stops there. Okay, you're only going to get this. It stops. There's nothing for the ammonia to react with because all of the halogenoalkane is used up. And that is why we have excess ammonia. But to prove that, let's look at what it looks like if the CH3Br is in excess. So if the CH3Br is in excess, we're going to do exactly the same thing. One of those and one of those is going to make this. Okay, so one of my halogenoalkane, one of my ammonia is going to make our amine. Now, the amine is the yellow, and then our halogenoalkane is the red. Now, I told you in the previous slide that the halogenoalkane can still react with the amine because the amine still has a lone pair of electrons on it, so still acts in terms of nucleophilic substitution. So that means I will get a mixture of products, okay? A mixture of products. So the reason why I have excess ammonia is so that I don't get a mixture of products, I don't get my secondary, tertiary amines, okay? I only get my primary amine because all of the halogenoalkane is used up if you do it with excess ammonia. And as you can see here, the halogenoalkane is not used up, and so will continue to react with the amine if you have the halogenoalkane in excess. And that's really, really important. So I wanted to point out something else, okay, just before I do that as well. And I've mentioned this just briefly. Remember, if you're adding excess ammonia, another thing that will happen is there will be ammonia around with the HBr. And if there is ammonia around, and they tell you there's excess ammonia around, the actual other product that you can make is the ammonia, which is a base, acting with the HBr, which is a very weak acid. Okay, they come together and you get NH4Br. So that's just something to be aware of. If it is in excess, then this product can be made as well. Okay, and let's just go on to the final slide to explain the whole thing together. So, why is excess ammonia used? We have a secondary amine, we have a tertiary amine here. Okay, what it does, excess ammonia means that there will be limited further substitution. So, for example, I won't get this secondary amine, I won't get this tertiary amine, I would just get the primary amine. Okay, and that's because the primary amine still has a lone pair, and therefore the nitrogen can still accept a proton acting as a base, and which means you'll get these further substitution products. Whereas if you have excess ammonia, there will be only primary, or mostly primary amine, and that's why you do it. So really important there that you know that they'll just both won't be there, and if they're both not there, you'll get the primary, which is using ethanamine would be this case. The last amine preparation we're going to talk about is reduction of nitrobenzene to form phenylamine. So nitrobenzene forms phenylamine, and the conditions are tin and HCl. So if you're in the exam, again, what are they going to ask you for amines? A lot of the time they're going to ask you the conditions. The other thing they're going to ask you is the overall balanced equation for this. So let's just put this up into the corner and then start talking about the balanced chemical equation. Here is a nitrobenzene, and they can represent the reducing agent, okay, because this is a reduction, remember. Okay, you're adding hydrogen, so it's reduction. You can represent that as a H, and we've seen that in other types of reactions in chemistry. So all you need to do is think, well, how many H's am I going to add? First of all, you know that the oxygens are going to be removed. So that means 2 oxygens are going to be removed. So if 2 oxygens are removed, both of them are going to be reduced. So when you reduce oxygen, you make water. Okay, and that is why you are going to make water as a product. But remember, there are 2 oxygens, so therefore I have 2 waters. And that's really, really important here. Okay, so there's your 2. And then at the same time, now all you do is count the number of hydrogens that have been added. And there's 2 on the amine here, so there's 2 here, and there's 4 there, which means the number here, 2 plus 4, is going to be 6. Now, the only way they can complicate that is through making it so that there are more than one nitro group on a benzene. So it's really important that you can do this question with more than one group, and all you have to do, this goes up in 6s, so it'll be 6, 12, 18, that'll be 2, 4, 6. So, if we then put that up here and look at that look at an example of that kind of question and go through an exam tip, we can see that if they do vary, just multiply the H and H2O accordingly. So let's do this example. Can you do this example across the bottom? So if you look at it, there's one NO2 there, another one there, another one there. So there's 3 NO2s. Count the number of oxygens. There's 2, 4, 6. That means I'm going to have 6 waters. And if I have 6 waters, that's going to be 6 times 2, which is 12. So 12 hydrogens from the waters, and then add it to the 6 hydrogens that are on the benzene. 12 plus 6 is 18. And as I said, there are 6 waters. So it's really important that when you look at this, count the number of oxygens, make as many waters as that, and in this case 6. Okay, then count all the hydrogens that you've added on the NH2s and with the water, and that will be your number of hydrogens you add on the left-hand side as well. And this is the only way they can complicate this question.